The objective of this lesson is to solve differential equations using the method of separation of variable. To outline how I want to go about this, I'm just going to first explain what is a differential equation and review slope fields. And two, explain what does it mean to solve a differential equation, and then thirdly, how to solve a differential equation. So a differential equation is just an equation where the function you're looking at is the derivative. So each of these are the derivative of some function. And you can tell because the label is dy dx. And in the past, we have looked at how do we visualize differential equation or the derivative. And that visual representation is what's called the slope field. So each of these differential equation or derivative correspond to a specific slope field. So the slope field for this equation is this one here. And the idea of the slope field is essentially it just tells us what the slope is at every single point. So for example, at the point 0, 1 here, at this point 0, 1 here, that tells we can see that there's a mini tangent line that has a positive slope. So if I plug in 0, 1 into this equation, we'll get some positive value, and that's represented by this tangent line with this positive slope. And we can do that for all possible points, and you'll see each of those tangent lines create what's called a slope field. And you guys can see what the slope field for these other differential equations look like below. Now I'm going to move on to addressing the question, what does it mean to solve a differential equation? So to solve a differential equation, we're just basically trying to find the function that has this specific derivative. What function has the derivative 6x squared plus 6x plus 2? You guys can answer that question for this one because you guys know the process of finding the antiderivative, using the rule add 1 to the exponent and divide by your new exponent. That rule doesn't work for these two differential equations because we have x and y on the same side. So for these two, we'll have to use another method called separating a variable. You guys also know another method which is called use substitution. So when we're solving differential equations, sometimes you'll be given what's called an initial condition. So this is an initial condition here. What this allows us is for us to pinpoint a specific equation. Okay, so just to visualize this a little bit, I want to see what is the function that has the derivative with this specific initial condition, and I can visualize it this way. So if I change the initial condition, I could get a bunch of functions. You can see that the green function is changing. But if I want to specifically see what's the original function where one of its points is 0, 5, then the function would be this green one here. And I can't make it as close to 0, 5, but it will be something like this. So our goal is to solve this differential equation. Given this point, we're going to find the function, which is the solution, we want to find the equation of this function here. And we'll also be able to do it for these two other functions. And now we're going to move on to the third part where I'm going to show you how to solve differential equations, both reviewing the add 1 divided by new exponent rule, which will apply to this one, and then the steps for solving differential equation where that doesn't work, which you'll see through these two examples. First example, we're going to solve this differential equation, 6x squared plus 6x plus 2. So remember, when we're trying to solve a differential equation, we're trying to find a function that has this specific derivative. Since this derivative here is a polynomial, we can use the power rule for finding the antiderivative. So what we'll have to do here is add 1 to the exponent and then divide by a new exponent. So I'm going to add 1 to the exponent here. We're going to get 3. then 6 divided by 3. And then same thing for the other terms. And this 2 will become a 2x. Therefore, the solution is y, and it's y because this is telling us that this is the original function, and the equation simplified would be 2x cubed plus 3x squared plus 2x, and then we'll need a plus c here because it could be, any constant could be here. When we take the derivative, it will get back no term, so that's why it's not missing here, so we need a plus c here. So what we're looking at, this one, we have a plus c. This solution is called the general solution. So this could, this is a general solution because this c could be anything. Now, since we have what's called the initial condition here, we can actually pinpoint a specific equation. And to pinpoint that specific equation, we'll have to use the point that's given and plug it into the general solution, which will help us find a specific c. So I want to go ahead and do that. I'm just going to write the point, the initial condition as a point 0, 5. So our x here is the 0, and then the y is 5. So I want to go ahead and plug it in. So it's going to be 5 equals 2 times 0 cubed plus 3 times 0 squared plus 2 times 0, and then we have the plus c. I'm going to simplify this. If I simplify this, I'm going to find a specific c value here. So this is going to work out to be 5 equal, all these terms, it could become 0. So that tells us that my c value is 5 when the initial condition is 0, 5. So what I can do now is from the general solution, I can get what's called a particular solution. And then my c was the plus 5. And now what I'm looking at here is the particular solution. And just to go back to the idea of slope field, remember that this is the slope field for this differential equation or this derivative. And what we just found here, the particular solution, the 2x cubed plus 3x squared plus 2x plus 5, is the specific function that corresponds to this specific point. So the equation of this green function here that passes through the point 0, 5 has this equation right here. You guys don't have space for the slope field, but I wanted to just give you a visual representation of what we're trying to, what this represents and what the differential equation, how the differential equation is represented. So just to conclude, the solution to this differential equation with the initial condition of 0, 5 is y equals 2x cubed plus 3x squared plus 2x plus 5.